There's an object in this galaxy that could wipe every credit card on Earth, from halfway to the moon. It weighs more than the sun, it fits inside a city, and if you got within 1,000 kilometers of it, your atoms would stop being atoms. It's not a black hole. We tend to rank cosmic threats by size. Black holes get the headlines, supernovae get the documentaries, but there is a class of object that physicists quietly describe as the most magnetically extreme thing the universe is known to produce, and most people have never heard its name: a magnetar. The magnetic field of a typical fridge magnet measures around 5 milliteslas. An MRI machine, one of the strongest magnetic devices in a hospital, runs at 1 to 3 Tesla. The most powerful sustained magnetic fields humans have ever created in a laboratory top out around 45 Tesla. A magnetar's field measures around 10 billion Tesla. That is not a typo, that is not a rounding error, and the consequences of a field that strong, what it does to space, to light, to matter, and to anything remotely biological, are not metaphors. They are physics. Measured, documented, published. That's what this video is actually about. To understand why a magnetar is what it is, you need to follow the death of a massive star. Not a star like our Sun, but something 15 to 30 times heavier. When a star that size exhausts its nuclear fuel, gravity wins catastrophically. The outer layers explode outward in a supernova, one of the most energetic events in the universe. But the core, compressed beyond any pressure you can intuitively grasp, collapses inward. Protons and electrons are forced together into neutrons. What remains is a ball of pure neutron matter roughly 20 kilometers across, the size of a mid-sized city, containing more mass than our Sun. This is a neutron star, already one of the most extreme objects in physics. A teaspoon of its material would weigh roughly 1 billion tons on Earth. Its surface gravity is 200 billion times that of Earth's, and it spins, faster than a kitchen blender, in some cases, dozens of times per second. Most neutron stars are extraordinary but stable. They radiate, they slow down over millions of years, they age. A small fraction of them, the ones that form under specific conditions of rapid rotation and your particular dynamo process in the collapsing core, emerge with something else entirely. A magnetic field amplified beyond any scale the rest of the universe routinely produces. In February 2025, researchers at Newcastle University published a study in Nature Astronomy showing the specific mechanism, a Tayler-Spruit dynamo in the proto-neutron star, that allows certain neutron stars to generate these extraordinary fields during their first seconds of existence. The field doesn't come from somewhere outside. It is generated internally, in the first moments of the star's new existence, by physics that amplifies magnetic energy the same way a rapidly spinning generator amplifies electrical current, only at temperatures and densities that exist nowhere else in the universe. And that field is not a passive property, like color or mass. It is active. It interacts with everything around it. It reshapes space. It splits light. Here is the number that stops physicists: 10 billion Tesla. In a field that strong, physics itself behaves differently. X-ray photons, light, can split in two or merge. This isn't theory, it's been observed. The vacuum of space around a magnetar becomes birefringent. It bends different polarizations of light differently, the way a crystal does. And matter, any matter, begins to change shape. That word will mean something specific in about 30 seconds. The magnetic field of a magnetar would be lethal at a distance of 1,000 kilometers. Not because of heat, not because of radiation, though there is plenty of that, because of what a 10 billion Tesla field does to the atoms in your body. Atoms are built around electron clouds, the electrons that orbit atomic nuclei and make chemistry possible. Those electron clouds have shapes. Those shapes determine how atoms bond, how molecules form, how proteins fold, how enzymes work. In a magnetar's field, those shapes distort. Electrons are forced into elongated orbital paths, spherical atoms stretched into thin ellipses, then into something approaching cylinders. The geometry that makes chemistry work breaks down. Your nervous system, which runs on electrical charges moving through molecules, stops. Your proteins, which fold based on molecular geometry, unfold or misfold instantly. The bonds holding your cells together, covalent bonds, ionic bonds, hydrogen bonds, all depend on electron geometry. 1,000 kilometers away from a magnetar, you do not burn, you do not freeze, you dissolve at the atomic level, your body's chemistry ceasing to function before any other effect reaches you. The Museum of Science in Boston describes it plainly. Within 1,000 kilometers of a magnetar, the magnetic field starts ripping electrons off the atoms in your body. What remains is a cloud of atomic nuclei. That is not science fiction. That is the confirmed physics of what 10 billion Tesla does to matter. There are roughly 30 known magnetars in our galaxy, probably many more. We only detect them when they're active, and magnetars spend most of their lives quiet. One of them sits on the far side of the Milky Way, in the direction of Sagittarius, somewhere between 30 and 50,000 light-years from Earth. Its designation is SGR 180620. It was identified as a magnetar candidate in 1998, when the Rossi X-ray Timing Explorer satellite measured its field at roughly 10 to the 15th Gauss, 100,000 billion times the strength of Earth's magnetic field. For most of the 1990s and early 2000s, it was a known object, studied, catalogued, monitored by X-ray satellites as it went through its cycles of activity and quiet. It had already produced smaller flares, outbursts detectable from Earth. The community knew it was among the most active magnetars in the galaxy. Then, in 2003 and through 2004, its X-ray output began climbing, brightening. The persistent emission roughly doubled in luminosity compared to its historical baseline. Researchers noticed. They were watching. What they couldn't fully anticipate was the scale of what was building. December 27, 2004, 21:30 UTC. On the far side of the Milky Way, a magnetar's crust fractured. Magnetic field lines snapped and reconnected. In approximately 0.2 seconds, SGR 1806-20 released energy roughly equivalent to what our Sun will radiate in the next 250,000 years. The pulse of gamma rays crossed 30,000 light-years of space. And then, at the speed of light, it arrived here. Every gamma-ray and X-ray instrument in orbit was watching different parts of the sky when the flare arrived. It didn't matter. Within milliseconds, every detector that was on the day side of Earth triggered simultaneously. Most of them saturated instantly. The initial spike, the first 0.2 seconds, produced the highest gamma-ray flux ever measured from any cosmic source at that date. Instruments designed to measure the most violent gamma-ray bursts in the universe were built with sensitivity ranges calibrated for events thousands of times fainter. This spike was off the scale. What came after the spike was, in its own way, even stranger. A pulsating tail of X-ray emission that lasted more than 6 minutes, modulated at precisely the spin period of SGR 1806-20, the rotating magnetic field of the star sweeping past Earth like a cosmic lighthouse, over and over again. And here is what makes this event the most important data point in the case for why magnetars are the most extreme objects in the known universe. SGR 1806-20 is between 30 and 50,000 light-years from Earth, not nearby, on the other side of the galaxy. And yet, the gamma-ray flux from its 0.2-second spike was more than 1,000,000 times stronger than typical cosmological gamma-ray bursts, the most violent explosions in the universe, which come from billions of light-years away. The flare was detectable bouncing off the surface of the Moon. Several instruments recorded the reflection. It came from the wrong direction, the Moon, before anyone had processed where the primary burst originated, and it disturbed Earth's ionosphere. The dayside ionosphere, the upper layer of Earth's atmosphere that radio waves bounce off, the layer that GPS and communications satellites depend on, was hit by a pulse of ionizing radiation from a magnetar 50,000 light-years away. 6 orders of magnitude, a factor of 1,000,000 change in the ionization density at an altitude of 60 kilometers, measured by ground-based very low-frequency radio monitoring stations, confirmed by satellite. This was not a nearby event. This was not a locally violent phenomenon. A magnetar on the far side of our galaxy reached across 50,000 light-years and measurably changed the chemistry of our upper atmosphere, from a burst that lasted a fifth of a second. Now think about that in the other direction. If SGR 1866-20 were 10 light-years away, not 50,000, just 10, the flare that disturbed our ionosphere from the far side of the galaxy would, at that distance, deliver a dose of radiation comparable to the worst-case scenarios in mass extinction models. The 2004 event didn't threaten us. The geometry of the galaxy is, in this respect, on our side. The nearest known magnetar is roughly 1,000 light-years away. But nearest known is doing a lot of work in that sentence. We have found 30 magnetars in a galaxy of 400 billion stars. For decades, we had a theory about where magnetars come from. In 1993, physicist Robert Duncan at UC Berkeley proposed that certain superluminous supernovae, explosions 10 times brighter than ordinary supernovae, could be powered by a newborn magnetar spinning down in their core, dumping rotational energy into the explosion like a cosmic flywheel. The theory was elegant, it fit the data, but nobody had ever watched it happen in real time. Then, in December 2024, a star 1 billion light-years away died, producing a superluminous supernova called SN 2024 AFAV. Astronomers at the Las Cumbres Observatory network tracked its light curve in real time. And in the data, they found a chirp. The oscillations in the supernova's brightness were decreasing in time interval, exactly as predicted by Duncan's magnetar spin-down theory, including a subtle signature caused by general relativity as the newborn star's precessing accretion disk fell into the field. It matched the model published 16 years earlier. For the first time in history, astronomers had watched a magnetar being born, in real time, 1 billion light-years away, confirmed in a peer-reviewed paper in Nature in March 2026. And here is what that birth observation tells us about the object in question. The newborn magnetar in SN 2024 AFAV powered a supernova 10 times brighter than any ordinary stellar explosion. Its magnetic field, in the first seconds of existence, was already amplifying energy output on a scale that rewrote what we thought those explosions could do. Magnetars are not a curiosity at the edge of astrophysics. They are engines. We just confirmed we can watch them switch on. 30 known magnetars. In a galaxy of 400 billion stars, across a disk 100,000 light-years wide. We find them only when they're active. They spend most of their lives silent. The survey of our own galaxy is incomplete, in ways that matter for this specific question. There may be hundreds, possibly thousands, sitting quiet, in the dark. The nearest known one is roughly 1,000 light-years away. Here's the honest shape of this story. Magnetars are real. Their field strengths are measured. The 2004 flare from SGR 1806-10 happened. It was recorded by dozens of instruments, and its effect on our ionosphere is documented in peer-reviewed geophysics literature. The 1,000-kilometer lethal radius is confirmed physics, not a made-up number for dramatic effect, based on what a 10 billion Tesla field actually does to electron orbital geometry. And we now know, as of a paper published in Nature in March 2026, that we have watched one born. Confirmed. Live data. None of this means magnetars are about to hurt anyone. The geometry of the galaxy, 30,000 to 50,000 light-years of distance, is our insulation. The nearest known magnetar is 1,000 light-years away. That is an enormous, safe buffer. What it means is that the universe contains objects so extreme that the rules of chemistry, the rules your body runs on, simply stop applying in their vicinity. Objects that, from the other side of the galaxy, can touch our atmosphere with a fifth of a second of effort. The universe is, on most days, astonishingly quiet and safe. Then, every few years, something on the far side of the Milky Way blinks, and every instrument we have notices. If that makes you want to understand what else is out there, there's a comet currently crossing our solar system from another star, carrying chemistry that formed around a sun that may not exist anymore. That story is next.